A couple of days ago, we had the 60th anniversary of the first human presence in space. And that marked the beginning of a new era with new applications of this space exploration that are growing ever since. And now we use the space satellites for many different purposes, either for exploring the space, for example, the Hubble Space Telescope, or the Planck satellite that is observing the cosmic microwave background, as well as for ground-based purposes, for example, GPS, or the giving the opportunity for faraway locations to have internet. And that is the project that we are starting right now, to provide schools a possibility to have access to the internet even if they are far away from the ground-based grid. So since this project is directed at schools, there is an educational part of it. Therefore, I would like to touch upon a question that is not purely academic, but very educational. Namely, the problem, what is the difference in the flow of time between the Earth, where we are now, and the satellites? I will take as an example the GPS satellites. They have very well-defined orbits. Therefore, it is easy, quote unquote, to calculate the difference. And it is actually two conflicting and opposing contributions. First of all, there is a difference in the flow of time because the satellites are rapidly moving with respect to us. The orbit of a GPS satellite is around 20,000 kilometers above the surface of the Earth, which means 26,000 kilometers from the center of the Earth. We are now 6,400 kilometers, so there is a difference. And they are orbiting the Earth during 12 hours. Within 12 hours, they are making full circle. Therefore, one can easily calculate that if they are on the orbit 26,000 kilometers from the center, that their speed is around 4 kilometers per second. So we could make the distance between Warsaw and Poznań, for example, in around a minute. So this is one contribution. They are very fast in comparison with us. Therefore, the special theory of relativity that was proposed by Einstein and very, very well tested up to now is that the fast-moving objects, the clocks are slower with respect to us. So in a sense, since they are much faster than we are, their clocks run slower. But on the other hand, there is a second contribution that Einstein in 1915 proposed as a new theory of gravity that replaced the gravity of Newton. Namely, in this theory, which is also very, very well tested, we have the phenomenon that the objects that are closer to larger mass, like we are closer to the Earth, have the clocks that run slower than the objects that are far away from the mass. The satellites are far away. As we said, they are 26,000 kilometers from the center, and we are only 6,400 kilometers from the center. And this makes our clocks run slower. Therefore, these two opposing contributions, we have to ask, we can calculate this, that what is the contribution of one and the other? And it turns out, when we plug in the numbers into special theory of relativity, that the clocks in satellites should run 7 microseconds per day slower than the clocks on Earth. 7 microseconds per day. It's not very much, but it's very easily measurable because the satellites that we are talking about, namely GPS satellites, have very, very precise atomic clocks on board, and they can measure such differences without any problem. But there is the second contribution that we mentioned, namely from the general theory of relativity, from the theory of gravity of Einstein, that if we plug in the numbers to this theory, it turns out that since we are closer to the Earth than the satellites, our clocks should run slower by 45 microseconds per day. So therefore, the net result is that our clocks on Earth runs 38 microseconds per day slower than the satellites, than the clocks in the satellites. One may say it's very, very small difference. It's a very small difference. Why should we care? But it turns out that the GPS system, which is based on the comparison of the atomic clocks on different satellites, when we switch on the GPS system, we know which satellites are where, and we receive the signals from them, and we compare the time clocks, the time signals from different satellites. It turns out that the whole system would desynchronize, would be completely useless after several days if we didn't take this difference into account. Therefore, it is a directly measurable difference. When we switch on the GPS, we already have a proof of both special theory of relativity and general theory of relativity. So when we apply this project to schools, it would be very, very good if the pupils, if the students, would know that they are actually measuring both special theory of relativity and general theory of relativity of Einstein. Thank you.